Okay, I think we're live. All right, everyone. Welcome to the last lecture of distributed summer. Today, to sort of close things off, I'm really thrilled we have Michael Keiblinger from Prime Intellect. Michael sort of consistently publishes some of the most interesting C++ and low-level systems content that I see on Twitter. I don't think this is necessarily a talk really about GPUs. It's more about Pickle and just generally fault-tolerant collective communication primitives over IP. So no GPU required, I guess. So yeah, and I'm joined today as well by another co-host Matej, who some of you might recognize from Kernelbot and Accelerate. So sorry, Michael.
Yeah.
Please, without further ado, please go ahead.
Yeah, thanks for having me. I guess, today I'm going to be talking about PCCL, the Prime Collective Communications Library, which enables fault-tolerant collective communications over IP, which is the library I've been working on at Prime Intellect. So yeah, maybe as a sort of chapter one, why even do this? So the motivation, of course, is to perform all reduces across the internet and tolerate and unwind basically all possible I/O failures, and expose primitives to implement many different distributed optimization schemes, ranging from naive DDP to Dilico, streaming Dilico, or eager Dilico with delayed application, where I actually do have slightly mathematically questionable, but application of dirty gradients where you actually do have full computation overlap, which in many situations is still very fine. And of course, one of the sort of big pluses, I guess, of PCCL is that we can guarantee bitwise identical results on all peers of all collective communications operations. And what this sort of allows is to facilitate independent advancement of the shared state, which includes model and optimizer state, to precisely the same end state, such that actually hashes will match. And this sort of just eliminates a whole category of problems as relating to, are these two sort of checkpoints the same? And it just sort of rules out peer drift in that sense. And one might sort of start to wonder here, well, okay, wait, GPU indeterminism, this and that, but we'll get to that in a second as to why it's not actually all that unreasonable to assume that. And in many cases, you can just facilitate perfectly deterministic shared state advancement even on the GPU with some fairly complicated kernels involved. So what does PCCL enable? PCCL enables, and this is sort of a mouthful from the paper, zero-copy bitwise deterministic interruptible pipeline quantized asynchronous collective communications. So I guess zero-copy meaning that we want to not copy on the way to the actual send call, at which point we are, of course, at the mercy of the kernel, whether or not there's going to be more copies on the way to the network card. But at least on the way there, we want to make sure that we don't copy the data and ideally directly reference the data from the user-provided tensor. And bitwise deterministic meaning, of course, that the collective communications operations guarantee the same results given the same inputs. Interruptible meaning that if some I/O failure were to occur because the neighbor just turned unresponsive, for example, then we want to be able to interrupt the all reduce, unwind properly, and return a failure status to the user, who then can decide whether or not to retry the operation. And pipelined, meaning that we're just implementing a textbook MPI pipelined all reduce with a reduce scatter and reduce gather phase. And because sort of the properties of the share phase, as it's also known, we can guarantee these bitwise deterministic results. And quantized meaning that we, of course, want to send in a lower precision than we actually have in our source array, if that is so desired. And while we do accumulate in higher precision internally, as you sort of move through the n-1 pipeline stages of the all reduce, where n is sort of the world size, the idea is basically that you sort of get a better and better statistical estimation of the quote-unquote true gradient, let's say, that we're reducing as the number of workers grows to infinity. Even though we're only ever sending, let's say, int8 reduced contributions which are dequantized internally. So yeah, and asynchronous meaning that we want to launch potentially many collective communications operations and want to await them at a time of our choosing. So whether that be this step or next step that is basically up to the application developer, and this is sort of like very important for sort of overlapping. And yeah, like I said, all peers obtain bit identical all reduced results. And what this sort of enables as a second order effect is that the shared state is fully rederivable from all performed reduced results and an initial state. So I guess let's sort of go to the programming paradigm. Every sort of PCCL application, first thing you want to do is, of course, initialize PCCL, but then create a communicator and point it to a dedicated master. PCCL employs sort of a lightweight dedicated master, which doesn't really do a lot and doesn't really transfer a lot of data. It is really just there for acting as a central source of truth and facilitating or basically storing connection information and sort of facilitating the state transitions of the protocol as to make it really obvious what sort of to transition into and unwind once a failure actually does occur. So this is sort of just, I guess, a crucial sort of design decision to just make fault tolerance more practical. It employs what we sort of internally refer to as a micro-consensus scheme, meaning that basically many blocking PCCL API calls facilitate sort of basically a barrier and also agree to do, let's say, some operation next, let's say accepting new peers. Which gets us to the next point, which is that peers may only join when the pre-existing set of peers actually deliberately accepts new peers into the run. And this sort of happens periodically, let's say once per step, where every peer just calls PCCL update topology. And at this point, the world size can actually increase. Whereas throughout the rest of the code, you can just expect that world size will only ever decrease due to sort of ungraceful failures, but never increase. And PCCL Connect will basically, from sort of the connector's point of view, will block until you actually reach the accepted state, which could potentially take some time, but it's sort of a safeguard in that sense. So yeah, let's get to the shared state. So the shared state is essentially, it references all weight and optimizer states and is synchronized periodically, but one really shouldn't sort of think of this as data transfer that occurs periodically if content hashes and revision match. So because we do actually hash the contents of all those tensors, and basically send those hashes to the master, which then says, okay, great, does this match or does it not match? And if it decides, well, that doesn't match, then you will be paired with a random peer that does have a popular shared state. And then you will basically be sort of paired to reobtain the shared state. But ideally, application developers are sort of expected to facilitate deterministic advancement of the shared state per logical step. So that the synchronization actually always is just a no-op in that sense. So the reason why this is sort of reasonable is because, like I said, we're getting the same all reduced result on all peers. And if we sort of concede that we already have some initial state, let's say some initial model weight state that is the same on all peers, then we just apply that update. And if we can sort of do it once, then we can do it n times, and therefore we just sort of rule out a peer churn. We just rule out peer drift. And yeah, so let's move sort of on to the main loop. So a typical PCCL application sort of consists of the following stages, if you will. First, we accept new peers. So this is a deliberate call. At this point, all peers agree to let new peers into the run. Because the world size may have changed, it is best to ideally run topology optimization, which will launch some speed tests and sort of build a bandwidth matrix and reachability matrix. And based on that, we then form an optimal tour if that is computationally feasible. Yeah, afterward, we synchronize the shared state, but again, this is sort of ideally a no-op and is really sort of just there as a guard, and of course there to sort of make newcomers fall in line, which of course have a fresh model state. So in that sense, it's sort of solving two problems at the same time, sort of an initial checkpoint sort of obtaining system, if you will, and a periodic guard in a sense. Then we can do some compute work, which may involve a model forward pass and backward pass, which will yield a compute result. And then we will do some collective communications operations based on that compute result, which will yield a communication result. And then we advance the shared state using that communication result. And ideally, if everything goes well, then the synchronized shared state call of the next step will actually be a no-op, unless, of course, a newcomer joined, in which case we could be transmitting shared state, but it should never be the case that we actually are, for some reason, receiving some bytes, because what that would mean is that our shared state has become unpopular or dirty. Yeah, so additionally, all non-async PCCL functions are strictly blocking and consensus-based. So this sort of means that all peers must call the same method at each point in time and sort of act as an implicit barrier. And sort of an important rule is that never must the application branch such that different peers call different microconsensus facilitating PCCL functions. So sort of the worst possible case that you could do is say something like, if random.nextbool in the first case, PCCL update topology, and in the else case, call something completely different like PCCL synchronized shared state. That is one way to deadlock yourself. So, and this is sort of the first part of the main loop in action, sort of what we sort of refer to as the accept pump and invocation of the topology optimization. Like I already sort of mentioned, peers cannot connect to the master, or peers can connect to the master at any point in time, but they remain in the register state, sort of in quote unquote sort of a waiting lobby until they become accepted. And this happens when the pre-existing set of peers calls PCCL update topology, at which point you will be accepted into a run. The connector will unblock from PCCL connect, and you know that every other peer at this point is inside PCCL update topology. And this is also sort of really important for sort of reasoning, sort of like where in the control flow you are when writing such an application, because we'll get to why in a second, but there's some strange footguns that if you're not careful, you can sort of accidentally deadlock yourself. After having accepted new peers, we of course call optimized topology, which could take some time depending on how many peers you have and how many new peers joined, because the edges that we do not yet have in the bandwidth matrix will be requested by the master, and then sort of a whole bunch of speed tests will commence. And once we have that data, then an ATSP solver will either form a precise or heuristic solution. And of course, you can add something like sort of a min world size sort of guard here, and sleep ideally, or something like that if you did not yet reach some minimum world size that you set, for example. Now, it's actually really important that this sort of looks somewhat like this. So if, let's say, you were to do something like, okay, great, I'm going to have outside my main loop, before I even fall down into the main loop, some second loop where I sort of wait for my core world size to be reached, and only then fall down into the main loop, then this has some very interesting quirks. So for example, let's say you have a minimal world size of 4, then 2 leave, but those 2 are already in the main loop, and now if there was another newcomer, that would be peer 3, who thinks that he has to wait, while the pre-existing set of peers is not in a control, like is not from control flow point of view in at a line of code where it actually cares about that limit. So again, it will by chance just call some PCCL function next, let's say synchronized shared state or something, and which will not match what the other peer wants to do, which is update topology, and then you sort of have a deadlock. So it's again sort of really important to reason about that even in the case where you don't explicitly branch, you can still accidentally branch. So yeah, and already sort of talked about this shared state. What does this look like? It's just basically a call. You call a synchronized shared state, And there's a few strategies. There's PCCL enforced popular, which will make the popular hash, or the most popular hash will get distributed to all peers, essentially. Yeah, there's some others like send only, where you deliberately say, at this point, I should only ever be sending shared states, which in some cases you want to do, and you actually do want to have that error in case the master cannot actually facilitate that. But yeah, during shared state synchronization, all shared state content is hashed using a sort of simple non-cryptographic purpose-built GPU optimized hashing function called simple hash internally. Yeah, again, if we sort of have content mismatch, then retransmission occurs to prevent peer drift. This is this is not really a very strong hashing function. It's really just there to just add sort of peak memory bandwidth to the point that that's possible. Reduce over some data with some very trivial bit shifting operations, and just obtain a hash which is good for the purposes of detecting slight data mismatches. So yeah, a best practice application should of course assert that after an initial sync, no further shared state reception occurs. So as you can see, sort of right here, after we've exceeded sort of after the initial sync has already run, then we assert that no further bytes should ever be received for any future shared state synchronization calls. It might be the case that we do transmit data, so tx bytes might not be 0, but all that really means is that we were chosen to actually distribute our shared state to somebody else who just joined a run. Yeah, as the next thing, let's get to performing collective communications operations. So we want to basically, because this is fault tolerant, we want to retry collective communications operations until a successful state is achieved. Now, this might fail for many reasons. Let's say if a peer drops, then we want to unwind correctly to the user's call site here and return an error status. Sorry, excuse me. That the user can respond to by either retrying or deciding to abort. And quantization can be enabled, as you can see right here in int 8. Yeah, this is sort of a trick to save bandwidth. And like I said, world size can change after a collective communications operation has been awaited, so it should be reobtained. So you don't want to have any sort of dirty application state where, let's say, your world size doesn't actually match the actual world size, which, if you're branching based on that world size, might result again in sort of this accidental divergence in code paths. So yeah, what's the motivation behind topology optimization, which is this this word that I've already talked about. So what you can see right here is a good topology. Here we have some sort of locally connected peers, and all of them are first connected via a sort of slower WAN link. It's not there isn't a full any-to-any reachability matrix here. Every one of those peers can talk to any of the other peers. But is it wise to do so if what you're doing is a ring reduce? And the answer is no. So you want to minimize the amount of times you want to, you're doing a hop over the slow link, where here you can sort of see, okay, we're actually sort of doing that only once, and I guess sort of the wraparound at the end, which is implied by the tour. But this is a very good topology. What would be a bad topology is this. So in this case, we literally have a hop over one basically all the time. But if that happens to be just the join order of the peers, and if all we're doing is just keeping the order in which peers join as our sort of tour order, then this is sort of what we're going to get, which is very suboptimal. Now, we don't just actually care about sort of the very obvious case where peers are locally connected, and they're sort of a slow one link, but also sort of cases where, okay, great, there's some peers in Europe, there's some peers in the United States, and point-to-point speeds can vary drastically. So we just sort of want to route around sort of the speed test characteristics of the specific set of peers that take part in our run. Yeah, also data centers often have high-speed Ethernet and often bind to public IPs directly. So what that means is that packets addressed to computers in the same data center can very often be delivered locally without bouncing the gateway, because the switch really doesn't care if there's a private IP or a public IP in the header, as long as it learns the IP MAC address combination. So in many cases you can sort of just run PCCL on public IPs and still sort of like get this hybrid benefit of, okay, great, some of those actually, like some of the hops of the overdues will actually be just fully locally delivered. PCCL will also take partial peer-to-peer unreachability into account. So let's say if a peer A cannot ping some other peer B, then the route will be constructed around this sort of unreachability, if that is possible. If that is not possible, then the peer that attempted to join that sort of brought us into this situation will be kicked, which is sort of the only reasonable thing that we can do. Fault tolerance means fault tolerant. Fault tolerant as a word gets thrown around a lot, but it rarely actually means fault tolerant. We can't have a situation where a run is brought down by some random IO failure. We're on the internet, things can go wrong. Packets get dropped all the time, random timeouts everywhere. So we want to really tolerate any sort of IO failure, and all error paths must be handled correctly and gracefully, which is easy in theory and hard in practice. We'll get to sort of the difficulties there in a few slides. Yeah, so the headline sort of for PCCL was 45 gigabits all reduce over the public internet. And when hearing this, one should naturally sort of go, how? And the answer lies in something called per flow fair queuing. So when you're establishing, let's say, cross-continental TCP connection, one usually observes really low speeds, like sort of in the hundreds of megabits. But this isn't really because you don't have fast enough internet. You might just have perfectly fine uplink, but it's just that routers decide to say no. This is usually because packets associated with the same flow or connection don't get to sort of monopolize the bandwidth, which is sort of by design. But also, secondly, what's sort of influencing this is that just TCP windowing itself gets less efficient as round trip time increases. So, the famous example is that the fastest TCP link to the moon you can establish with sort of the default 16-bit TCP window limit is like 0.22 mbits. And even sending UDP datagrams is not sort of the best alternative, because some routers really heavily deprioritize your traffic if you're sending UDP. So the solution here is really just opening a lot of connections, and by just internally dispatching to a lot of connections, PCCL can sort of achieve these high throughput rates, and you can sort of see this almost comical scaling law of throughput as the number of connections increases. Because we don't necessarily care about order, it's like we're just dispatching some fragments to a bunch of connections, and the probability that any one of those actually is not stalled because of packet reordering or something like that, is sort of the likelihood of such a stall happening decreases with the number of connections increasing. And so this is sort of the middle ground that PCCL targets. In sort of the more distributed case of just the US and EU, we get 25 gigabits.
Actually, Michael, do you mind if we just pause for a few questions?
Yeah, sounds great.
Yes. I do have a few questions. As you were saying, there are specific strategies for the synchronizations. And I wonder, did you observe some specific scenarios when one would be way more useful than another, and why would that be, and which one would that be? Let's say you just want to train pre-train a model, which one would you choose and why?
So the shared state synchronization strategy is really just there as a means to essentially assert that at a particular site of invoking synchronized shared states, you should never be, let's say, receiving shared state. So for example, if you're doing something like eager Dilico, where you sort of have and a sort of a pipeline that is started essentially one step in advance, you sort of have to properly insert the peer. And for this scenario, actually, one shared state synchronization is not enough, because you sort of need to eavesdrop on the sort of result of the previous all-reduce that you were not part of because you just joined, and that all-reduce started last step. So in that sense, you need actually two shared state synchronizations, once to sort of obtain the weight before, and once after the sort of dirty update was applied. And in this case, the site that is providing the shared state should never be in a scenario where it is at sort of the other side of hash popularity. So one might imagine a situation where more peers join in a single step than pre-existing peers, and in that case, you end up with a scenario where you would essentially be destroying your shared state, because you're now out-popularized by the newcomers, which, if they happen to have, let's say, some set seed, then this will essentially destroy the run. So the reason why the strategy exists is to specifically navigate this problem that you say, no, the newcomers receive only, and the pre-existing peers send only, and the master must facilitate that this is the case, ignoring any notions of hash popularity that might interfere with that.
Okay, thanks. Also, I do have a question regarding the topology-aware optimization. Like, is that aware of only the topology of like the network itself, or can you somehow specify, like, for example, when you do distributed algorithms, some are more latency. Like latency is more important, some bandwidth, and so on and so forth.
Yes, right now, the only thing that actually counts is the speed test that we perform. I guess one could sort of replace this with a ping, but that is currently not supported. But yeah, in most cases, you really want to sort of maximize bandwidth and sort of have as much data sort of in flight as possible. As you can sort of see, the number of connections is, as you scale that, you do get most of the bandwidth if you have, a good uplink, and this is sort of the regime that you want to be in.
So I had like one last question. I think then we can go to YouTube chat, which was so you talked a lot about like bitwise reproducible training, and one thing I found interesting was like at least like this is not something people really expect from even like GPU programming, where there's less things that could fail. And so could you sort of maybe help me bridge the gap between, like, you kind of seem to be demanding something harder in an even harder domain. And so like what's going on? Is it just that like in GPU-based programming, there's a skill issue, or is it like there's certain things that people aren't thinking about? Yeah, like what's going on here?
It's really just about sort of being careful with torch operations. Like, you can perfectly do this with torch just fine. Like, there's many examples in the PCCL GitHub repository that just literally use the actual atom class and still accomplish this. So it's really just about like being really careful with sort of the lockstepping that the PCCL sort of actually by design sort of force upon you. And if you sort of follow the best practices, you sort of get it for free. So in a sense, the signatures were basically designed around like guiding you there, such that you always have something that fails in a very discernible place. If you don't quite get it right yet. But in essence, element-wise operations, sort of in the most trivial case, element-wise operations don't really induce any true GPU and determinism. So it's actually not that unreasonable to expect that. And I have some slides on that topic later. But the TLDR for now is that, at least for Atom, it should be sort of, it shouldn't be that surprising that this is possible, that if you have some gradients and you drive an optimizer step with those gradients, that this is essentially possible without GPU and determinism.
Okay. Yeah, there was one question in chat as well. So they're asking, how do you ensure the RNG are seeded correctly when you have a dynamic working group?
So the RNG for, let's say, the model initialization, I think that's what that means. I mean, it's sort of like the API is sort of designed around this not mattering. It just matters in a sense that you don't want to accidentally get outpopularized by newcomers, which all have sort of the same shared state if you do have a set seed. So in a sense, it is potentially wiser to use random seeds. Because basically the very first shared state synchronization that happens will choose one of the possible peers to sort of be the designated shared state, and that will be distributed. So in that sense, it doesn't really matter too much how you seed the RNG.
Yeah, thank you.
I think we can keep going.
Yep.
All right. So yeah, so in a more sort of localized scenario in sort of Western Europe, which I guess sort of in terms of distance is not really a lot, but you can achieve 45 gigabits, and I guess this was likely because the 50 gigabit NIC of the machine that we tested this on. But as you can see, as you sort of get more co-located, you need less connections, less concurrent connections to achieve high throughput. Yeah. And yeah, we talked a lot about fault tolerance, but like, what does fault tolerance actually mean? So I guess the best way to sort of show this is with a video. So let's see if that plays. I think it does. Okay. So what you can see right here is lots and lots of processes spawning, and they contribute to a very tiny MNIST run here, which where the step takes quite a short amount of time. So it's a very high frequency training loop. So any sort of IO failure that occurs from those peers randomly getting killed must be handled in such a way to not cause any hiccup. And as you can sort of see from the prints, there are no hiccups, which I should say in this case is sort of a little bit cheating, because the socket APIs behave a lot nicer when you're doing stuff over a local loopback, because you are sort of more instantly informed when a peer drops. But the same principle occurs or basically applies when you're actually dealing with a wire, except that it just takes a little bit longer to actually discover, okay, great, that peer is actually dead. But yeah, so this is at least showing the lower level bound, in a sense that if there wasn't just this nature of socket APIs being socket APIs, that this is essentially the amount of peer churn we can sustain without any hiccups. So yeah, let's get to sort of chapter 2, agony. So what does it take to create something truly fault tolerant? And the answer is, if you're building something based on top of socket implementations, well, you're dealing with a set of loosely related, similar-looking APIs implemented on various operating systems that all vaguely promise to implement the same thing, that is UDP and TCP connection, a communication in ever so slightly different ways. And if all you want to do is just open a connection and send some data, then I guess you would be sort of fine. And you will not hit any of the rough edges. But every OS has some also important revisions as to what started out as the Berkeley Sockets API, even though Microsoft basically only implemented WSA, the Windows Socket API, by accident, which essentially copied the Berkeley Sockets API, but because Microsoft is Microsoft with a completely different error handling system. But yeah, by accident, I really mean accidental, because Microsoft never really planned on supporting the emerging internet. They really just sort of had slight delusions of grandeur in the 90s that they were going to do sort of their own thing. So the fact that they adopted this API is actually sort of a miracle. But by copied, I literally mean copied. So there's a reason why you have an Etsy host file in your system32. Now, while one could sort of proclaim victory and say, hooray, all major operating systems use roughly the same socket API heritage, it's really just that, it's heritage. And the implementation, of course, is vastly different on every operating system. And if you think that code you wrote on Linux will compile on Windows, you would be mistaken, even though the APIs look strikingly similar. And even if the code does compile, the behavior you encounter might drastically be different. For example, here's a basic example of demonstrating a common misconception about how sockets work. So for example, when you're dealing with an actual normal file descriptor, when you issue a write, at least after a flush, you know that it has hit the disk, or at least the NVMe's DRAM cache or something like that. So unless there's like a power outage or something like that, it's persisted. Now for socket file descriptor, this looks a little bit different. So here we do some basic validation on some packet data that we receive, and then decide whether or not it's bad data, and sort of send the courtesy error message and close the connection as a result. Now, in this case, we sort of do already know that the client is malicious, so we don't necessarily care too much what happens to that client. But in this case, this data that we just sent in sort of the sort of leading up to the close might not arrive. And the reason for that is because we issue a reset, and reset causes the other side to essentially drop all handling of any pending data. This is in some scenarios very bad, because essentially some non-very well-defined region of previously issued sends is potentially at jeopardy of just never arriving. So you want to do a more graceful shutdown, where you use the SO linger socket option. Now there's even some quirks with that, because like how long do you linger around for the other side to hack your data? And the answer is sometimes for a very long time. So you want to also potentially place a timeout on that. So there's even more fun. Yeah, so let's maybe get to another very fun pattern. Socket implementation quirks #2. Let's say you have some thread which receives data from a socket, and you want to do that basically forever until you shut down. But you want to, of course, have a method to actually commence that shutdown. So here you have an interrupt function, and in this case, we simply close the socket FD. Now, you can't really kill the threads. There's not really such a thing. You aren't also really supposed to. And many higher level languages may pretend that you can, but if a method is truly blocking in kernel space, you have to get the kernel to voluntarily relinquish control. And so either the kernel voluntarily gives you back control, or you're never seeing that next line. So any sort of like if not running break kind of thing that you might want to do will be of no use at all. But one might sort of imagine, surely if you close the socket, then it doesn't make sense to receive more data. But the answer is that's not what happens. On many implementations, you actually need to add shutdown read write, and only that way RecV actually unblocks. And I guess this is sort of like a really sort of important thing to highlight, that or a reason why you should really have CI on every operating system when you're writing something like this, because you might sort of prematurely think that this is fine on some operating system, and well, it does compile on the other one, surely therefore it works. And the answer is no. You really truly have to test all of these cases on every operating system, because you might encounter even something. You might even encounter behavior differences inside Docker versus outside. It's really strange. Now in practice, how you actually close a socket looks even more horrible than that. So you want to even add a RecV timeout, which actually has an influence on how long SO lingers around. And only then do you close, or do you shut down both sides of the connection, and then you close the socket. Now, in practice, this is really just the tip of the iceberg of socket implementation quirks, and I can report there's way more fun ahead, as illustrated by sort of this meme here. But this alone, of course, is sort of still not enough for fault tolerance. So just being aware of these quirks doesn't make things fault tolerant, even though by now you might sort of recognize some of the patterns of sort of like network applications failing in particular ways, which might sort of plausibly be explained by these sort of API quirks, which may not be handled properly in the code. But that alone is not sufficient to actually create a fault tolerant system that can actually recover from all of these failure states. If you encounter any such failure condition, you must properly unwind it. And this sometimes isn't just as simple as return to caller. sometimes you must initiate some very complicated recovery procedures and make sure that you do not leave any sort of dirty state behind. The sort of application state must be exactly as sort of you found it before you issued your call. Sometimes the recovery procedure might even involve some packet sending. For example, if you are doing a ring reduce, you have exactly one neighbor, or sorry, two neighbors. You have one predecessor and one successor, and you're basically sending and receiving to just two sockets here. Now, when some other peer at the other side of the ring decides to become unresponsive, you're not necessarily informed of that. You're not necessarily aware of that unless you're explicitly informed of that via a packet. So this means that you actually do need to, in the case where you discover such a failure condition, report to master, say, this guy just became unresponsive. And then the master can reconfigure the topology accordingly, and then basically tells the peers to reestablish peer-to-peer connections. But there's some sort of there's a lot of sort of footguns with these sort of cross-connection packet handling chains as a sort of potential footgun, because you essentially have zero guarantee of sort of cross-connection arrival order. Let's say if some peer A sends a packet to the master, which then sends some packet to another peer, which then, let's say, initiates a teardown of the connection with that other peer. That peer might not yet be aware that we're about to tear down connections. The chain from peer A to the master to peer B might be faster than even if you're just sending in rapid succession. It's really just it comes down to ping. Then any sort of scenario where the packet, I guess this is a little bit complicated to illustrate, but essentially you must establish a consensus for basically everything. Otherwise, you sort of get spooky packets from that might seem unsolicited. So this, while this sort of might seem obvious as a consequence of ping, the implications for how you structure your protocol are not immediately obvious. So this is also a reason why we do have these very sort of predefined sort of state machine-esque transitions as orchestrated by the master. And now one might answer, or one might ask, isn't this sort of trivial? Isn't this just good programming? Just handle all the errors, bro. And the answer is yes. And it's one of those things that's easy in theory and extremely hard in practice. And in some scenarios, if your system is too permissive, it cannot even be fault tolerant theoretically. For example, the first attempt at implementing PCCL allowed peers to join at any point in time. So this meant that sometimes peers would join while collective operations were already sort of ongoing. So to continue the application loop, they would essentially have to partake in those that are yet to start, and needs to have a valid update to contribute into the all reduces that are yet to come. But the only way for that to happen is if you know the weights that that update is based on, which you obtain with a call to synchronize shared states, but that only runs once per step. So, and in this step, that phase has already passed, and before you know it, you have a literally unimplementable API. And through this really just happens a lot quicker than you may think. Just through some innocent API declarations, you have accidentally implied promises that you simply cannot keep. Now within sort of the world of ML, I guess people are certainly no stranger to sort of declaring overly ambitious APIs and then have no shame in throwing exception in your face if even though you sort of would be perfectly within reason to assume that the code you just wrote is actually legal. But I guess I'd sort of take a moment here to appeal to reason for a second and hope that we as an industry sort of stop doing this, because I think ML has sort of grown out of the just a bunch of dirty scripts sort of phase into serious infrastructure. And I think we should start to hold ourselves to the same standards as the rest of the industry and don't just randomly fail. So deterministic advances of shared state. So PCCL can guarantee bit identical results on all peers. And what that, of course, allows one to do is facilitate a fully deterministic advancement of the optimizer state. And this is, of course, sort of trivially possible with most optimizers that are simply element-wise expressions. Yeah, because those very trivially do not induce any GPU indeterminism. But even matrix multiplications asserting same block size, kernel configuration, anything that is sort of like relevant from the auto-tuning point of view would be deterministic in many cases. So is flash attention forward, by the way. It's right there in a README. It says it's deterministic. There's even a flash attention backward that is deterministic, but that needs a little bit more memory and is a little bit slower. But even something like the muon's Newton-Schultz iterations are actually unproblematic and will result in deterministic independent advancement because sort of these iterations are really just mapmols and element-wise ops. Now you might be wondering, does NVIDIA guarantee this? And the answer is absolutely not explicitly. But we can be extremely certain that this is de facto the case. So I guess after 27 slides in a GPU mode talk, well, we actually first talk about GPU stuff as opposed to networking stuff. But in short, we find that NVXBEF behaves identically across GPU generations from the GTX and ATI all the way to the B200. And for NVXBEF, the potential surface of breaking change is actually much larger because it's actually implemented in libdevice.bc, which is an LLVM bitcode module, which decomposes into quite a lot of smaller NVVM, LLVM IR instructions, which then map to actual PTX instructions. So we're dealing with somewhat of a high-level construct here, and yet the behavior is A, fully deterministic, and B, the X to Y mapping persists across GPU generations. So as you can see, if we sort of hash the input-output space of all possible bit patterns, and sort of how many nands you get, how many ins you get, along with the checksum, then we would get the exact same output on GPUs ranging from the GTX and ATI all the way to the B200. And you can sort of push this point a little bit further if one truly sort of cares. If one avoids certain classes of kernels, for example, those that rely on atomic contention for reduction, let's say, then you can achieve fully deterministic training on GPU, where basically the run will always result in the same hash for the weights after some n epochs in. And here you can see a CUDA implementation of MNIST training on a 4090 in a fully deterministic fashion, despite utilizing kubeless gem kernels. Now, in this scenario, hashes will actually differ between GPU generations because of the behavior of tensor cores, but MMA instructions in this respect are actually sort of a rare exception among PTX instructions. As far as I know, at least in parts, the motivation behind TileIR was to sort of partially restore some of the compatibility that was lost there. I would still not sort of bet on the numerics, but at least then the instructions aren't literally different. Theoretically, this could even be scaled to transformer language models if one truly cares when you use a deterministic flash attention backward. And while PCCL only really relies on the optimizer step being deterministic, like you can have data load indeterminism as much indeterminism there as much as you please. That like isn't really a concern to PCCL. But it's just if you truly own the training loop and sort of can rule out these sort of very unfortunate sort of things that might induce indeterminism, it's actually very possible. And I guess with that, I'll leave it to some more questions, I guess.
All right. Sweet. If folks have any questions in chat, like now's the chance. Otherwise, Matej, I'm not taking it.
Yeah. If I may, you were saying about the compatibility between systems and distributions. Like this might be just like last time I did this was in my networking class, which was 4 years ago, and I was quite a noob back then. But I remember that having like a let's say compatible behavior even between distributions and like versions of Linux was quite painful. I remember we had on a server we had some weird BSD like distribution, and I just import my Ubuntu code there. So yeah, like how compatible it is, like to what extent, I guess.
So PCCL actually runs on Windows, Linux, and Mac OS. So we actually just bit the bullet and just basically we have CI on every single operating system. Some libraries we use actually are even tested on OpenBSD, I guess. But that's sort of the only way to, first of all, trust no one, don't use libraries, and test. That's basically the way to go.
So this question might be a bit self-indulgent, but like I was wondering if you could walk us through the iceberg that you showed for sockets.
Oh yeah. So I guess I guess the first sort of the tip of the iceberg is Nagel's algorithm, which essentially is grouping packets. So if you send lots and lots of small messages, this isn't really obvious. This isn't really optimal. So this will sort of internally group things together, and let's say in a game loop, this might cause trouble where you're sending like some very tiny packet that like says the player just moved, and it's like 12 bytes or something because it's just a motion vector or something like that, and it will just get grouped, and then you get these bursts of packets essentially of like lots of movement happening all at once, sort of. Write and close resulting in data loss is sort of the situation that I already talked about. Issuing writes and just unsafely closing places some writes that happened in the vicinity of that close at jeopardy of never being received. So, and the next thing I guess is keep alive is not a heartbeat. So by default, you will see some very strange behavior if, let's say, some peer dies and you're stuck in a reqv, and you're sitting there wondering why after like literally 2 hours you get your first timeout. This is literally what happens if you don't configure anything. So this is sort of this right here. So you do actually have to properly configure keep alive. Surprise sick pipe from send. So one might sort of imagine that, well, what could possibly go wrong sending? And the answer is, well, if the peer literally dies, then it's not just that you don't, it's that you don't just get like a return code. Like the sort of primary means of error handling for socket APIs is that you get some sort of error code that is below 0, but for send, you actually sometimes just get sick pipes, which is an actual signal, which will basically kill your process if you don't handle it, or you specified explicitly that you do not wish to get this signal with a flag. And again, this will sort of just be, and this will happen on some operating systems. So for example, on Windows, you have essentially this whole different WSA error handling system where you say, okay, great. Well, the reqv state is smaller than 0, but in reality, you still have to obtain like actually like the WSA get error code to actually figure out what's going on. Whereas sort of the same failure state would be represented differently on Linux, where it would just be, well, okay, it's -1 on Linux or something. Whereas on Windows, it's just like, yeah, it's some random code that happens to be less than 0 or something. But you also have to query this other thing. Or sometimes I think I even remember that sometimes they're just not being a status and the WSA error being set, which was some very strange behavior, but I wasn't able to fully reproduce what was going on there. But so there's some very, very interesting error handling quirks. So I guess the sort of the example that is most sort of presentable, I guess, here is the surprise sig pipe. It's not just a return code. It's like it will literally kill your process. So, and the next thing, time wait that processes can have alive sockets. So it might just happen if you don't use SO reuse address that you launch some server which binds to some port. You kill the process and you do ls off -i and the port, and you see something is still binding to that thing. How the fuck does that happen? And the answer is that that process, that socket is still in the time wait state. So it's the only thing that you can really do is not like you can even get rid of that socket. You just bind over that socket with reuse address, and the operating system will just decide to dispatch to that new socket and no longer forward to that old socket. But it's still there, and it will eventually exit. But you will have two things binding to that same port. And that's basically the only way that you can guarantee sort of like an actually non-annoying loop where you can just control C your server and make it restartable without just like having random bind errors. So that's
so there there isn't like an API for like, because I ran into this like sometimes where like I'm like just like there's like basically like I used to call them like immortal processes or something, like, or just like immortal sockets. Is there like no API to kill this? Like basically what do you do in this situation if you're stuck in a time wait?
I'm not sure if there's like any way to actually get rid of the timeout, the time wait socket, but the solution in practice is always you literally just you reuse the address
Took
port
over, right?
combination. So this is literally the solution in that case. Like most servers do actually use reuse address when they bind. So this is a fairly standard practice. But this is sort of the reason why. And yeah, close does not unblock recv is another one of those sort of foot guns potentially. And yeah, half closed drain behaves differently on Windows. So there's sort of like this pattern that you shouldn't really be doing, I guess, that is a potential replacement to a so linger, where you shut down one side of the connection and drain all data that is still yet to come. And that sort of guarantees the same thing that a so linger does, sort of. But there, I'm not sure fully what's going on, but there's something where like Windows is sending different TCP messages and resulting in different timeout behavior, which is really strange. So you shouldn't really be doing that. And yeah, so, and I guess Solinger can stall your close without a recv timeout. And I guess at the very bottom, the listen backlog in combination with TCP quick-ACK can result in like literally sort of half-established connections where the quick-ACK connection thinks it has a connection, and the server is like, nope, I rejected you because of backlog. So that's sort of one very strange thing that was really nasty to debug. But yeah, that's sort of the tip of the iceberg, I guess, or the tip of the iceberg all the way to the bottom, I guess. Although I'm not saying there's more.
Yeah, if I may, I have a question, like kind of related to this. Like, how do you test these things? I remember that being a real pain in the ass for my networking project again. Like, yeah. I remember saying that, like, I don't care. Like, the teacher is not gonna test these. I can't even simulate it. Like, they're not gonna do that.
I guess the answer is the name of the chapter, which is agony. So the basically just trying to explain every sort of behavior that you see, trying to reason about the system from first principles, just what do you expect, when are your assumptions violated in the ever so slightest ways, and then just working backwards and yeah, sometimes just if that means, okay, great, deploy on the random machine that this happened on, see if you can catch it in the debugger, even if it means like hitting pause in the debugger, if you like, and with sort of like some I want to catch this timing now, like this specific point in time. But so it does involve some fair bit of trial and error, because most of the time the only thing that really the conclusion is usually just like you ignored something that you shouldn't be ignoring. So in essence, it's like once you sort of know what to look out for, it's like, well, then writing the code is simpler in a sense. It's more like that when you're just sort of like from a principle of least surprise point of view using the APIs, that the code that you write initially will not actually have sort of will not handle errors gracefully. Yeah.
Yes, there were 2 more questions in the chat, and that is, first one was, what about using an orchestrator to handle failover along a SIG pipe? I suppose that's related to this meme.
I mean, I guess what that would mean then is that we have to that we just concede that the process dies, I guess, which we don't want to do. Like, we don't want to just kill the process. Like error handling schemes that are essentially, some sort of recovery procedure where you launch another process, it gets really messy. You never want to sort of like be in that regime. So you always want to stay within, okay, I have my process. I will just handle the error and deal with it. You don't really want to be in a situation where it's like, okay, great, well, the process failed, but like I can like restart it or something. Like I'm pretty sure like TorchFT does something like they launch like a sub process that actually does the NCCL reduce, and they just kill that thing once the NCCL state gets corrupted because of when an actual failure occurs. So that's sort of like not the way that you want to approach things. Like this is just I think we should call it as it is. It's just NCCL just not being very very well implemented, and it should be handled at a different layer. It should never propagate that far.
Yeah, and that kind of the last question was how does PCCL how does it integrate with like Combs libraries such as NVSHMEM or other transport layer solutions, I guess?
I guess PCCL is sort of like a standalone product in a sense that you can't like there are Python bindings for it. You can use it with NumPy and Torch, but it's really just like this thing that is not by almost deliberately not trying to integrate with too many pieces of software specifically to sort of reduce the surface area of things that can go wrong. And I think the sort of the course would be, if there is a feature that we do need, then it should be implemented with respect to the existing sort of fault tolerance sort of mechanisms that exist in PCCL. So as like if you sort of mix and match sort of like things, like even if you do something like, okay, great, I have FSDP on one dimension and PCCL on the other dimension, where essentially you have like this 2D grid, which is something that I talk about in the documentation, where you have just the FSDP dimension over NCCL and a DDP dimension with, let's say, Dilico over PCCL. It's sort of a little bit, it does reduce fault tolerance in some sense, because if, let's say, you just hit the watchdog timeout from NCCL because, well, some peer died of the of the actual FSDP group, then well, I in PCCL can't really respond to that. It's just a blocking thing that I do not have control over. So in a sense, that could stall the run. It, of course, eventually will sort of unblock once you hit the timeout, but that does sort of reduce the fault tolerance if you do not actually disable this. So there's sort of trade-offs with everything that has sort of implicit behavior like that, and sort of the implications of that.
Michael, before we let you go, I do have one question. It might be a bit of a bait question, so forgive me, but like, which is like, I'm sort of really curious, like, for your hot takes on like where you think nickel could be doing a better job. Is it like a burn it to the ground kind of thing? Is it like more of there's a few things they wish they paid more attention to make the life of people that do fault tolerant research a bit easier?
I think it's just as simple as that. Errors should return error statuses and not fail in any other strange ways. I think that's just the only sort of general piece of advice that I can give. This has a lot of sort of implications for how you structure your code around that, but like I don't really want to like tell people how they should like design the systems when they deliberately decided to sort of like not handle something potentially for good reason. But I would say I might recommend it, but I wouldn't explicitly sort of just say, well, this is what we should do. Yeah, so from that point of view, just errors should return error statuses and not fail in any other strange ways, and design your APIs around that.
Yeah, I have I would say bait question as well. Like why PCCL? Like now you risk people that call NCCL nickel, which is me and apparently Mark as well, calling you pickle. Which, like,
the name. I guess like pickle, I think is already partially in use. So I guess it sort of like collides with the unsafe serialization library from Python. So
yeah. It's terrible to have two pickles in my code base, like.
Yeah.
All right. Well, Michael, thank you so much for coming on. So, folks, we do not have a lecture planned for next week. We had 6 lectures this week, so this would be more than enough content to carry you over. We have a hackathon happening in New York with Jane Street. So if you're interested, in these kinds of topics, I think you'll really enjoy it and you should apply. Otherwise, we'll see everyone in 2 weeks to talk about mega kernels. And again, Michael, thank you so much for coming on. We really appreciate it.
Thanks for having me.